Operation of PID for typical shape main engine. History of PID controller. The first evolution of PID controller was developed in 1911 by Elmer Sperry. However, it wasn't until 1933 that the Taylor Instrument Company, or TIC, introduced the first pneumatic controller with fully tunable proportional controller. A few years later, controlled engineers eliminated the steady state error found in proportional controllers by resetting the point to some artificial value as long as the error wasn't zero. The resetting integrated the error and become known as proportional integral controller. Then in 1940, TIC developed the first PID pneumatic controller with a derivative action which reduced overshooting issues. However, it wasn't until 1942 when Ziegler and Nichols tuning rules were introduced that engineers were able to find and set the appropriate parameters of PID controllers. By the mids of 1950s, automatic PID controllers were widely adopted for industrial use. PID stands for Proportional Integral Derivative is a controller loop mechanism employing feedback that is widely used in industrial controller system and a variety of other application requiring continuously modulated control. A PID controller is an instrument used in industrial controls applications to regulate temperature, flow, pressure, speed, and other process of variables. The purpose of PID controller is to force feedback to match a set point such as thermostat that forces the heating and cooling until it to turn on or off based on a set of temperature. PID controllers are best used in systems which have relatively small mass and those which react quickly to change in the energy added to the process. It is recommended in a system where the load changes often and the controller is expected to compensate automatically due to frequent changes in a set point, the amount of energy available, or the mass to be controlled. A good example of temperature control using PID would be an application where the controller takes an input from a temperature sensor and has an output that is connected to a controller element such as heater or fan. The controller is usually just one part of temperature controller system, and the whole system should be analyzed and considered in selecting the proper controller. The working principle behind a PID controller is that the proportional integral and the derivative terms must be individually adjusted or tuned. Based on the difference between these values, a correction factor is calculated and applied to the input. For example, if an often control cooler than required, the heat will be increased. Here are the three steps. First, proportional tuning involves correcting a target proportional to the difference. Thus, the target value is never achieved because as the difference approaches zero, so too does applied correction. Second, integral tuning attempts to remedy this by effective cumulating the error results from P action to increase the correction factor. For example, if the oven remains below temperature, I would act to increase the head delivered. However, rather than stop heating when the target is reached, I attempts to drive the cumulative error to zero, resulting in an overshoot. Third, derivatives tuning attempts to minimize the overshot by slowing the correction factor applied to as to the target is approached. PID controller problems example. Almost every process of control application would benefit from PID controller. Here are several PID controller problems examples. Heat of metals, ramp, and soak sequence need precise control to ensure desired metallurgical properties are achieved. Dyeing or evaporating solvents from painted surface. Overheating temperature conditions can damage the substrates, while low temperature can result in product damage and poor appearance. Curing rubber. Precise temperature control ensures complete to cure is achieved without adversely affecting material properties. Baking. Commercial ovens must follow a tightly prescribed heating and cooling sequence to ensure the necessary reactions to take place. That's all. Thank you.